Okay, we're going to do our last type of motion. So vibrational energy and its quantized values. So we're going to talk about a very idealistic model, and we'll see that it's not a perfect match for chemical bonds, but it's a pretty good model. It's called the harmonic oscillator. For the harmonic oscillator, the potential energy as a function of x is equal to 1/2 kf, so that's some force constant, times x squared. So what it means is if you extend the distance between the particles, it will get to a point where the potential energy forces you to return. You don't have enough kinetic energy to keep getting longer. Or if you compress it on the other side, it'll get to the point where it stops compressing and gets longer again. So you have a potential energy that's a function of Sx that looks like this. So when we write Schrodinger's equation, the kinetic energy is the first term, like we had for translational energy, h bar squared over 2m negative, second derivative of the wave function with respect to x squared, and then it would be plus this potential energy function times psi has to give you back E times psi. So that's a much harder differential equation just to look at as a chemist and decide what the solutions are, but mathematicians have solved this for us. And so the energies, they are quantized, and the energies, E as a function of V is a quantum number, 0, 1, 2. It's kind of hard because V, which I put here in red, and nu, the frequency, look very similar, but the energy is a function of a quantum number multiplied by Planck's constant times the frequency. And the frequency is a function of that restoring force constant, the Kf, and then the mass of the particle that's vibrating. So stop and do self-test 7E.1. The wave functions are given in a table, and they're a function of a Gaussian and a Hermite polynomial. So let's take a quick look at the figures that show us those wave functions so we can get an idea of what they're telling us. Number one, we'll find they have 0-point energy. Number two, we'll find that the particle can tunnel. And number three, we'll talk about something called the Bohr correspondence principle. So let's go to those. Oh, where did my... Oh, there we go. Okay, so when we look, okay, so here's what the model that we're solving. So we have particles that are vibrating, and when you go to the right, you're stretching it, and when you go to the left, you're compressing it. And when you talk about the middle at 0, that's what we would think of as an equilibrium bond distance. So the bond length would be defined as that distance. This shows you that the energies are quantized. So the smallest possible energy is 1/2 h nu, because energy is equal to V plus 1/2 times h nu. And if V equals 0, then the lowest energy is 1/2 h nu. And notice that they're equally spaced. So every time you go up a V, you go up 1 h nu in the energy. So it's an equally spaced set of energy values. When we look at the wave functions themselves, so on the left, it's the wave function. On the right, it's the wave function squared. Remember, the wave function squared gives us the probability, and the wave function just shows us the shape of the function. So when we look over on the wave function squared, the highest probability of finding the stretched mode of that system is at that equilibrium distance where x equals 0. Each time you go up, you get another bump. And we talked about the 0-point energy. Okay, I just want to make sure I cover those three topics. And so this says that when you're in the ground state, the most probable location to find the stretch in is at x equals 0. And so let's think about this. So when you're stretching it, stretches, 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 and then it has to stop and turn around, and then compress, 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 stop, turn around. So the locations at which you're going the slowest are at the X's, which are represented in blue. So when we're in the slowest energy state, these locations. So it would be more logical to think that when it's going super slow, it's going to spend more time as it slows down and turns around, slows down and turns around. So it'd be more likely classically to find the particles stretched at a distance where it's turning around. So very non-classical to find it at the point at which it's going the fastest. It's zipping through with all of its kinetic energy through that x equals 0 place. And you can see, let me make this a bigger. So when you look at this, when you're stretched right to the point on this blue line, that's the point at which all of the energy equals potential energy, and it should stop and turn around. But look at this, you can see that the wave function extends beyond that line. So it extends into a region where you don't have enough energy. You don't have enough energy to get through that potential barrier. So this says that the particles can tunnel. So for example, something like HCl, you might not have enough energy in a photon that is absorbed by it to break the bond, but it might tunnel. It might be able to break the bond, not by actually having enough energy, but by entering this classically forbidden region because the wave function exists there. So we talked about tunneling when we talked about the particle in a box, and all of our different shaped barriers in that section. So it's another example of tunneling. And then this is just a different way of looking at the wave function essentially and the probabilities. And then this is in comparison to this. So when we look at this, the ground state, very localized, highest probability to find it at 0. Next state, you can find it above and below 0, but not at 0. There's a node. So as you go up, you get more and more peaks. And when you get to a very high quantum number, you have peaks that look like this. And essentially, you get a more equal displacement with bigger peaks at the turning points. So this is Bohr's correspondence principle, that as you get to a higher excited state, it starts to look more classically. We said when we were here, it would make more sense to see it stretched as far as it would go or compressed as far as it would go, because those are the points at which it's going the slowest. And so when you get to a highly excited state, that is what you start to see. So like most situations, highly excited states, the quantum mechanical solution begins to look more like a classical solution. And that's it for vibrational motion. Next chapter, our topic 8, will go into thinking about how these solutions can be put together in order to have solutions for the hydrogen atom. So we want to go back and think about what we did in Chem 107, our understanding of also must have boundary conditions because we have quantum numbers, only allowed energies, and we'll see how we can use these solutions to understand those energies. Oops, so I just